Welcome, my friends. I'm so excited because in this video we get to talk about the paired t-test for dependent samples. So let's go ahead and get started. The paired t-test is unique in that it is a test that is used for dependent or paired samples. Before and after data naturally create dependent samples. The hypothesis test is applied to the difference of the two samples. So the best way to describe this is just to give an example. Let's say we have some sort of before and after data, such as maybe pre-test scores and post-test scores. So what would be happening here is each individual would take a test before they enter a class or before they go through some kind of learning module, and then they'd be asked to take the test again or some similar test after they have gone through and taken the class or gone through the learning module. And what we want to do is compare the post-test scores and the pre-test scores. So every single row of this data would relate to one individual. So this 60 would be person number 1, what they scored on the pre-test, and the 64 would be person number 1, what they scored on the post-test, etc. for all the other individuals. Now, right here it says the hypothesis test is going to be applied to the difference of the two samples. So what that means is we're going to take these two samples and we are going to subtract them. So what I've done here is I have taken the post-test scores and I've subtracted the pre-test scores. And this is what I'm going to label as the difference column, post minus pre. So I've taken 64 and subtracted 60 and gotten 4. I've taken 87 and subtracted 84 and gotten 3, etc., all the way down through the table. And these numbers are representing how much better each student scored on the post-test compared to the pre-test. So person number 1 scored 4 points higher, person number 2 scored 3 points higher, etc., all the way down through the table. And what we're going to end up doing is doing statistics on this final difference column. So for example, I might have x bar with a subscript d, which would represent the mean of this difference column. In general, anytime you see anything with a little subscript d, that's going to mean that it has been calculated based on this third difference column. So x bar d is the mean of the difference column, and SD would be the standard deviation of the difference column. Let's take a look at the hypothesis setups for our null and alternative hypotheses. So the left tail test would have mu sub d is equal to 0 in our null hypothesis, and mu sub d is less than 0 in our alternative hypothesis. Mu sub d is the population mean difference. It's kind of like saying if I had every single possible student's pre-test and post-test, what would the mean of the difference be? Or what would be like the average improvement that every single out of all the students, what would the average improvement be? That's kind of what this mu sub d is saying, right? And if the alternative was that mu sub d was less than 0, that's kind of like saying that on average these numbers are negative, which would actually mean people are getting like worse on the post-test compared to the pre-test. They've actually, on average done worse, which might not be the most appropriate hypothesis test for this setup, but in some cases the left tail test might make sense. So this would amount to finding a p-value in the left tail of the t distribution. We could also have the right tail test, which would be maybe more appropriate in this specific example, because this would be saying that, oh yeah, on average, people are actually doing better on the post-test compared to the pre-test. The mean is greater than 0 or positive. And this is going to amount to a right tail test, finding a p-value in the right tail of the t distribution. Or we could have the two-tail test where we're saying, well, we don't really know if there's improvement or disimprovement. We don't really know if there's been any change. So we're just going to have the two-tailed test where we have the not equal to sign in our alternative hypothesis, which would amount to finding a p-value that is split between the two tails. Here are the assumptions of the paired t-test. You must take random samples related to paired data, or a random sample related to paired data. So basically you have to have the same individual, usually maybe at 2 different points in time, or somehow you have some sort of paired data. Paired just means that every observation from your first sample can somehow be paired to the second sample, right? Which is what we had here, right? Each one of these test scores kind of related to the same individual, so they're kind of paired together, right? And that has to be the case in order to do this test, because otherwise the subtraction of the data isn't really going to be meaningful. You must also have at least 30 data pairs, or the difference variable must follow a normal distribution. This is kind of a central limit theorem type requirement that we've had in many other cases as well. In step 2, we're going to have to calculate a test statistic, which is going to be x bar d divided by sd divided by the square root of nd. Remember, anything with a d just means it's based on that third column of data once you've subtracted your two samples. We'll also need some degrees of freedom since we're using a t distribution, which is going to be n sub d minus 1. X bar d is the sample mean difference. SD is the sample standard deviation of the differences, and then ND is the number of data pairs, or you could say the number of differences. Now, I do want to also just note here that this is the same test statistic that we used before for the one sample mean. Let me bring that up. Actually, let me bring up this handout. So if we look at this this handout here, which you can find this in the notes to this video, or the description of this video, you'll see here for the one sample mean, we used a very similar kind of formula here, x bar minus mu divided by s over the square root of n. This really is the same formula, but just we have the d's on everything, and we don't have to subtract this mu. The reason why we're not subtracting this mu is because we assumed in our null hypothesis that the mean was going to be equal to 0. Basically, there was no difference between our two samples. So this really is, if you want to get technical here, this really is the same exact test that we did all the way back in the one sample mean. It's still the same test statistic. It's just that we're using it for paired data. All right, let's go ahead and look at an example. So this example says that students were given 2 different brands of gum. We have brand A and brand B. The students were asked to chew each brand of gum on 2 separate days and report when they believed that the gum had lost its flavor. We want to know if there is sufficient evidence to suggest that the brand A gum lasts longer than the brand B gum, and we're going to use a level of significance of 5% or 0.05. Now, it's important to mention why this is paired data, or why it makes sense to do the paired t-test on this data, and the reason is because every row represents the same student. Or in other words, basically the brand A time and the brand B time both relate to the same student. So this is student number 1 chewed brand A gum, and student number 1 also chewed brand B gum and had a time for each of those. If we had 2 different students chewing each brand of gum and then we were comparing it in that way, then it wouldn't really make sense to pair them up in the sample. So then we would be doing the independent t-test. But here, since we have the same student for each one, we're going to be using the paired t-test. One decision you're going to have to make at some point is how you're going to be subtracting the samples, because anytime you do a paired t-test, one of the steps is going to be to subtract your 2 samples. So are we going to be taking the brand A times and subtracting the brand B times, or are we going to do it the other way around, take the brand B times and subtract the brand A times? Well, it doesn't really matter which way you do it. You can do it either way, but it will end up, if you have a one-tailed test, it's going to switch around the sign in your alternative hypothesis. So depending on which way that you set it up, you're going to have either a left tail test or a right tail test, or vice versa. Now, it doesn't really matter which way you do it. You're going to get the same p-value either way, but you do have to make a decision. So in this case, we're going to decide to let our difference be taking the A times and subtracting the B times. Basically, what that means is any of the differences we get will be representing how much higher the brand A time is compared to the brand B time. Okay, no matter how we do the difference, our null hypothesis is always going to be that our mean difference is equal to 0. Basically saying that there's not really a difference between the 2 brands of gum. They are both have about the same chewing time, I guess you say, or flavor time, right? There's not really any difference, or the difference is 0 on average. The alternative hypothesis is where it can be a little bit trickier, right? So this is where you have to kind of consider how you've defined your difference, and also kind of the wording that they have in given in the problem. So the problem says, is there sufficient evidence to suggest that brand A lasts longer than brand B? Okay, well, if brand A was lasting longer than brand B, then that means when we subtract them, and we subtract them in this order, we take the A time and subtract the B time, we're going to actually have to get a positive number, right? Positive number would represent that the A time is higher than the B time. Make sure you understand that. Maybe pause the video and think about that for a second, why that would be the case. If the A time was longer than the B time, which is what they're suggesting, then when we subtract them in this way, we're going to get a positive number, right? You take a bigger number and you subtract a smaller number, you're going to get a positive number. Positive numbers are greater than 0, so we're going to have a right tail test in this case. If we were to switch these around and had B minus A, then we actually would have had a left tail test. Either way, we're going to get the same final answer, but that would kind of switch things up in this step. Next, we can go ahead and go to our TI-84 calculator to kind of get the results. So I'm going to go and grab my calculator. Here it is. I'm just going to move this to the side. And we need to type these numbers into our stat list. So the way we can get to our stat list is we can press the stat key, and then the very first option for edit. And if we already have numbers in there, we can go ahead and clear those out. So I'm going to scroll up to list 1, press clear and down arrow. Go to list 2, clear and down arrow, and then I'm going to go ahead and just type in all of those numbers. Okay, for sake of time there, I just went ahead and typed in all of those numbers, but you may want to pause the video to type in those numbers if you're following along. And then once we have all those numbers plugged in, we can go ahead and go to list 3, and then we can basically subtract list 1 and list 2 so that they are in list 3. Remember, we have to do the difference here, take the A time and subtract the B time, so that's what we're doing in this step. To do this, we're going to have to hover over list 3. Note, you can't be down here. You have to be hovering over list 3. We can press second and then 1 minus second and then 2, and you'll notice down here it's going to say list 1 minus list 2, and then if we press enter, we are going to basically get the difference between all of those kind of immediately. So 424 minus 286 is 138, 1219 minus 757 is 462, etc., all the way down. Now we need to do statistics based on this third list. So we can go ahead and press stat. We can arrow over to calculate, and then we can do the 1-bar stats. And then we can switch the list to list 3. If it doesn't already say list 3, we can press second and 3, and that will change it to list 3. And then we can go ahead and calculate to get our kind of results. And those are also the results that I have here in the PowerPoint. So we had our X bar of 292. That's really X bar D. It's a sample mean difference. So that's X bar D, and the bar isn't really completely showing here due to the PowerPoint error, but this should be X bar, the big bar over top with the 292. That basically says that the brand A time was on average 292 seconds more than the brand B time, so that seems like quite a bit. We also have a couple other numbers that we need from here. So we have the sample standard deviation of the difference is 474.81. We have the sample size, which was 10, and then we can also find the degrees of freedom, which is 9. Next, we can move on to step number 2, which is the calculations, finding the test statistic and the p-value. So here is the test statistic formula. We need to take the x bar of the differences, which is 292, divide by the standard deviation of the differences, which is 474.81, and divide that by the square root of the sample size, which is 10. So I'm going to show how I would type that into my calculator here. I could just take it and just put it exactly how I see it there. Maybe I'll move it over so you can see the numbers over there as well, in case you're still checking where those came from. We have 292, which was our sample mean difference, divided by the standard deviation, which was 474.81, over the second square root of 10. And if we close the parentheses there, we're going to find that we get approximately 1.94 for our t-score. And then from there, we could go ahead and draw our distribution. We got a t-distribution here with 0 in the middle, which is always the case for the t-distribution, and 1.94 somewhere to the right. And we're trying to find that area in the right tail, since we have a right tail test. So we can find that using the tcdf function from the calculator. So we could go in here and we can press second distribution. And then we could go down to the tcdf option, which is option 6. We could put the lower bound of 1.94 and then the upper bound of 1,000. Or 10,000, it doesn't really matter. And then we can go and do the degrees of freedom, which are 1 smaller than our sample size. It's going to be 9. If we do that, we see the p-value is about 0.0422, which is exactly what I have right here. All right, finally, we can go ahead and, so that's the area in the tail there, and we can go ahead and do our decision and conclusion. So to make our decision, we need to compare the p-value to the level of significance. In this case, our p-value is 0.0422, which is less than or equal to the 0.05 level of significance they gave us here. So you know as how the saying goes, if the p-value is low, the null will go. I'm sorry, I said that wrong, didn't I? If the p-value is... If the p-value is low, the null has to go. That's what it's supposed to be, right? And if the p-value is high, the null will fly. So in this case, the p-value is low. It's lower than 0.05, so the null has to go. We're going to be rejecting the null hypothesis, right? The p-value is less than or equal to the level of significance, so we're going to be rejecting our null hypothesis. All right, finally, we can go ahead and write our conclusion statement using the template that we're hopefully familiar with at this point. So at the 5% level of significance, there is enough evidence, since we rejected the null hypothesis, we're going to say is rather than is not, to suggest that the brand A gum is lasting longer than the brand B gum. It seemed like that was the case from our sample. 292 seconds more for the brand A compared to the brand B is really what this is saying, and that was enough evidence to say in the population that that trend is also probably going to hold. All right, so let's go ahead and give you a problem to try. So we have a group of randomly selected runners on a track team, and they're going to run the 400-meter dash twice. Once prior to the study taking place, and then a second time after a week of drinking Speedy Runner Magic Juice, which does not sound like that would be within the confines or the rules of maybe 400-meter dash running. Okay, so based on the given data, which we have here, is there sufficient evidence to suggest that the runners are running faster with the juice than without. And we're going to use a 5% level of significance and assume that we have a normal distribution since our sample size is not at least 30. So go ahead and pause the video and see if you can go ahead and do the entire hypothesis test. So first step, see if you can set up the null and alternative hypotheses. Second step, see if you can get the p-value, test statistic, and then finally make a decision and write a conclusion. I'll be back here in just a second to get you the hypotheses, but I'm going to let you do the rest on your own. So go ahead and pause the video and see if you can complete the problem. Okay, so the problem does tell us here that we should have the difference as being post minus pre. So really what that is doing is saying like how have the times really changed after they've taken the juice compared to before, right? And since these are time in seconds, if we have a negative number, that's actually going to represent an improvement, right? So if I ran faster, like this second person ran faster, 2 seconds faster, when I take the post time and I subtract the pre time, I'm actually going to get -2, right? So negative numbers here are actually going to represent faster times, right? So if we go back here, they want us to see if the runners are running faster with the juice than without. So running faster is actually going to be where we have the lower times, or I guess the negative numbers here, right? So actually we're going to end up having a left tail test. So when you go ahead and you set this up, you're going to have an alternative hypothesis that's going to have a less than sign, because less than is actually going to indicate an improvement, like a negative number in terms of post minus pre. Okay, so go ahead and try that problem out, and that's all I have to say for this video. So I will see you in the next one.